Well, we've had Dr. Rob Carter speak once before, so I'm not going to go through his bio. But we're in for a treat tonight. If you've caught his first session, it was fantastic. He's going to give this talk, and then we're going to have Gary Bates come in and give you an alien intrusion experience. And then Dr. Rob Carter is going to come back again this evening for that night owl session, that special talk that isn't in your schedule. So 9:45, you're going to want to come back from that because he's got some mind-blowing stuff he's going to share. So why don't you guys give it up for Dr. Rob Carter.
Well, as you all now know, my name is Robert Carter. You're about to hear a story that has taken me more than 20 years to put together. This goes back to my, with my first 200-gallon saltwater aquarium. Then to my over 500, I lost count of 500, but over 500 scuba dives in Florida and Belize and the Bahamas. And eventually to my Ph.D. in coral reef ecology. Now, this has not been an easy process, however, for I've had to unthink much of what I previously learned. Much of what I learned contradicts the history given to us in the Bible, especially the creation account. You know, the book of Genesis tells us in beautiful narrative how God created the entire universe in 6 days about 6,000 years ago. During that 6-day work week, God first created light, and then time and space. Then he separated the oceans from the skies. Then he filled the land with plants. Then he created the heavens with the sun, moon, and stars. On the 5th day, he filled the seas and the skies that he created 3 days earlier. Likewise, on the 6th day, he filled the earth with animals, and then his ultimate creation, man. But we're going to focus on day 5 of creation week. Genesis chapter 1, verses 20 through 23 says this. And God said, let the water swarm with swarms of living creatures. So God created the great sea creatures and every living creature that moves with which the waters swarm according to their kinds. And God saw that it was good. And God blessed them, saying, be fruitful and multiply and fill the waters in the seas. And there was evening and there was morning, the 5th day. Okay, so we're going to talk now about some of the creatures that God created on this day. We're going to talk about one specific group of critters, but most people don't know what I mean when I say the word coral. You think rock. I think animal. Like a lot of people collect shells, but very few people consider the animal that used to live in that shell the beautiful snail. So let's figure out what a coral is. Well, first of all, a coral is an animal. But it's not just any animal. It's a simple animal with 3 layers of tissue and some characteristic stinging cells. Well, that puts it in phylum Cnidaria, along with the jellyfish and the Portuguese man of war and hydroids and all sorts of things like that have stinging cells. But it's not just any cnidarian. Corals belong to a group of animals called anthozoans, or flower animals. Now, the anthozoans are broken down into 2 main groups. We call them the hexacorals and the octocorals, because their tentacles come in sets of 6 or sets of 8. The hexacorals, most of them have a skeleton. Most of the octocorals do not. So here we go. If we want to talk about coral reefs, we're going to have to focus on a subdivision of the hexacorals called order Scleractinia. How you doing with these big Latin words so far? Scleractinia means hard anemone. And this order can be broken down to several main families that can be distinguished by shape or color or habitat or behavior. Corals are animals, by the way. They have behaviors, even if they can't move. And some of these animals are stunning in their beauty. A lot of what you see in this photo are Scleractinian corals, or recently deceased Scleractinian corals. They've got a rich diversity of shape, color, texture. It's amazing animals. They have a lot of things in common, especially at the most fundamental level, because corals follow a basic design that's based on the presence of a polyp. Some corals, like this one right here, are solitary. It's just a single polyp. But if you take that polyp and you split it in half, you can reveal the basic biology of these animals that do amazing things. You can see a ring of tentacles and a central mouth and a simple stomach, a 2-way stomach, so anything that doesn't get digested comes back out the mouth again. Now, if that looks like an upside-down jellyfish to you, it should, because jellyfish and corals have the same basic anatomy. They're both based on the polyp structure. But this particular polyp, being a coral, being a scleractinian coral, is sitting on top of a piece of limestone. It made this rock. In the process of growing, it extrudes calcium carbonate from its lower tissue layer, and as it grows upwards, it secretes calcium carbonate underneath it, so the animal is actually growing an exoskeleton. We have an endoskeleton. Corals have an exoskeleton. But if you look carefully, you can see these two things of tissue to the side, and these are going to connect to the next polyp in the series. Well, that raises some interesting questions. See? That raises some interesting questions of what actually a coral colony is. Well, we're stuck with this polyp-based form. Therefore, corals are limited in how large they can grow. This is an example of a large mushroom coral, maybe 6 inches, 20 centimeters wide. That's about as big as they can get, a little bigger sometimes. But you'll notice already that his mouth is being distended because he's trying to adapt to this huge thing with all these tentacles that are passing food into the mouth. So corals, because they're in the polyp structure, they can't get much bigger than that if they keep that form. And so, in order to get larger, very often this one animal will divide itself up into a multi-mouthed sheet of tissue. Now, the animal is only a few millimeters thick, but it can cover a large surface area. I have seen single coral colonies larger than this stage, several meters in height, that made a whole patch reef all to themselves, and it was just one giant colony with thousands upon thousands of mouths, but one animal. So really interesting. They're not like normal animals. Normal, whatever that means. Now, corals come in many shapes and sizes. This beautiful specimen is my absolute favorite. This is Dendrogyra cylindrus. They have their tentacles out in the daytime, and they wave in the wind. It's absolutely amazing animals. And you can notice that this animal has sent up these stubby branches to increase its surface area, so it can capture more food, capture more light. Here's another branching coral. This is Porites porites. I grew this one in my lab by taking a pair of wire cutters and going break, and taking some super glue and gluing it to a plastic screw, and then putting it in a plastic holder in my fish tank. I grew hundreds of these this way. It's really neat. They're very modular animals. In fact, I grew all of these animals in my lab. Probably a dozen different species. In fact, I grew those sea urchins in my lab. And yes, those spines are pointy, and when they hit your hand, they break off and they leave a black scar in there for days, weeks, sometimes months. And then the next day, you put your hand in the tank, and it happens again. And so that's the life of the marine biologist, I guess. Now, when most people think of coral, they usually don't think of the animal. This is Montastria favulata, the great star coral that forms many reefs in the Caribbean. Now, when they think coral, they usually think of the skeleton. This is a skeleton. We took a hole saw, went up to a coral colony, and drilled a hole in it, and then put it into a piece of PVC and put some clay around it, and it grew up out of the PVC and made this lovely thing. And then a disease came through my tanks and killed this colony. I was very sad because it was 5 or 6 years old by the time it died. I mean, from the original colony. But if you take this and you zoom up on that skeleton, you can see some beautiful architectural details. And sometimes coral colonies or coral species are kind of hard to tell apart, especially if they're in the same family. And so people have taken to measuring these microscopic little details, the width of this and the length of that. In fact, my first paper I ever wrote was dealing with this very thing. I microscopically examined 3 different coral species with my partner, and we concluded some various conclusions about these 3 species. It took a lot of work and a lot of measuring. But they're amazing stuff. Now, one more interesting fact about the tropical scleractinian corals. Now, I just said tropical scleractinian corals. Did you understand what I just said? Can you believe that I just said that word and you understood it? Because 5 minutes ago, you just said what? Okay, scleractinian means hard. The hard corals, the calcium-producing corals. Well, they're actually algae farmers. These little buggers are photosynthetic. In fact, it wasn't until the middle 1800s where people said, oh, those aren't plants, those are animals. Oh, okay, so now corals are animals, and they are animals. But inside them, they have thousands upon thousands, and you can see this brown. Can you see the polyp here? This is a baby that I collected in the wild, and I settled, and I took this under a microscope, and all these little dots in there are called zooxanthellae. They're algae that live inside the coral. Under a special microscope, I took this photograph. This guy here is only about 1 millimeter or 2 tall. This is tiny. This is actually from a colony of Ph.D. asteroides with little teeny polyps. And you can see this reddish glow in here. That's from the chlorophyll that's in all the zooxanthellae that live in the coral. The zooxanthellae take sunlight, and they convert it into sugars. Carbon dioxide, sugar. The coral says, yum, yum, thank you for the sugar. The algae says, yum, yum, thank you, or thank you very much for a place to live. Now, there's some debate about whether the zooxanthellae infect the coral, or if the coral has a zooxanthellae in prison. But no, this is a symbiosis, a beautiful relationship that allows these animals to live in what is otherwise a desert. Because there's no food in the open ocean. There's hardly any nutrients in the open ocean. It's the world's giantest desert. And yet, if you go into the open ocean, you can find a patch of ground that's close to the surface, and it was probably, at least in the past, would be covered with scleractinian corals. You know, the more I learn about these animals, the more I want to shout with the psalmist. For you, O Lord, have made me glad by your work. At the works of your hands I sing for joy. Beautiful. Now, we know what a coral is, right? Not just a rock, it's an animal. Let's talk about what a coral reef is. But first, let's define what a reef is. See, the question of what is a reef depends upon whom you ask. To a biologist like myself, a reef is a community of organisms. I'm more concerned with functional ecology. So a 2,000-year-old coral reef has about the same functional ecology as a 100-year-old lava flow that has corals that have encrusted, and sponges and algae and fish have recruited to it. It looks about the same. You can't tell from the surface necessarily which one is older. But to a geologist, they will give you a very different answer. Geologists are concerned with structure, shape, form. So to a geologist, a reef is something in the rock record, usually made of limestone, that appears to have been made by living corals or clams or algae or sponges that has some thickness to it. But the word reef is a nautical term. It's something that I have to worry about that's just under the... Wow. It's just under the water surface, and it's something I could run my ship into and rip my hull open. That's what the original word reef meant. But since then, the term has broadened, and now we have what is called a coral reef. So my basic definition of a coral reef is a pile of calcium carbonate, limestone, made or secreted by corals, but helped out by algae, clams, and a few other things. Now, whether or not this includes a community of living organisms depends upon whether or not it's above the water surface, in the water, or way down deep, because there are coral reefs that have sunk below the ocean surface, and they call them drowned coral reefs. All the animals are dead, but they're still sitting there way under the water. Now, more on fossil coral reefs in a minute. First, coral reefs are generally restricted to the tropics, the place where the water never drops below 20 degrees C, or for you thermodynamically challenged, that means 68 degrees Fahrenheit. Now, the 20-degree isotherm, we call it, is shown here in blue. You'll notice that the west coasts of South America and Africa are not as warm as they could be. That's because cold water currents come up the coast, and they prevent coral reefs from forming there all the way up close to the equator. Pretty cool. And there's other places in the world where the water's just too hot, like the northern Persian Gulf. Coral reefs can't grow there because the water's too warm, because above 30, 32 degrees Celsius and below 20 degrees Celsius, that relationship between the coral and the algae breaks down. It doesn't work anymore. So tropical coral reefs, scleractinian corals, are pretty much restricted to that band right there. Now, this map shows modern reef locations. You'll notice there's a lot of reefs that aren't in that 20-degree isotherm, because there are a lot of cold water and deep water coral reefs that most of these have actually been discovered. There's a gigantic one off the coast of Ireland. Scleractinian corals do not absolutely need clear tropical waters. Many live in dark and cold places. And sometimes they form extensive underwater structures. But the corals that harbor zooxanthellae, the little algae, they require a certain water clarity, water chemistry, and water temperature. And those conditions are generally met in the tropics or places in the world where a tropical current goes northwards or southwards into the temperate regions like Florida, Okinawa, or the southern Great Barrier Reef in Australia. So I'm going to ignore for the rest of this talk a lot of these deep water and cold water reefs, and I'm going to focus on the main coral reef areas of the world. Now, the question of how a coral reef grows is a very good question, is it not? In fact, it's critical for our explanation of how we get coral reefs in the world in only 6,000 years. Well, first and foremost, coral reefs are generally limited by the growth rate of the animals and plants that build them. How fast do corals grow? Well, it depends on which species you're examining. Some grow very quickly. This photo appeared in Creation magazine about 17 years ago. It shows a coral growing on a shoe. Now, a lot of people were shocked to see that, but I wasn't that shocked. That is Poeciloptera damicornis. It's a very fast-growing coral. In fact, I started with 25 colonies of this species that I bought from a guy in Miami who was growing them in his garage. And I brought them to my aquaculture facility at the University of Miami, and within a couple of years, I had thousands of colonies by breaking and gluing, grow, break, glue, 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 grow. It was crazy. In fact, these guys started reproducing in my tanks. I had thousands of coral babies all along the edge of my tank, right at the water level. I had to scrape them off to get rid of them. They were choking the flow to go down the drain. Crazy. So, the growth of a reef isn't the growth rate of a single coral. It's the accumulated growth of all the animals on the reef. So you have to account for fast-growing and slow-growing corals, parrotfish eating the corals, storms breaking the corals, the accumulation of sand and debris on the reef that forms a reef structure over time, and the death of the coral colonies. So all of a sudden, a lot of creationists over the last couple of decades they say, well, this coral over here can grow 1 foot per year. 1 foot per year, 3,000 years, that's 3 kilometers. But it doesn't quite work that way. And a little later, I'm going to show you different ideas, I think better ideas, of how to explain rapid growth of coral reefs. See, our challenge is to explain things like Australia's Great Barrier Reef. This stretches for hundreds of miles, thousands. It has thousands of reefs linked together in an amazing array. There are hundreds of species of corals. There are hundreds of species of fish. There are thousands of species of mollusks, that's snails and octopuses and things like that. This is an amazing place. Well, how do we explain this in a young Earth context? That's the challenge. This is a typical cross-section of a reef. Corals grow upwards and outwards. And the reef is shaped by physics, like waves, tides, storms. The reef's also shaped by chemistry, the availability of calcium carbonate, and it's also shaped by biology. So that very complicated thing all put together makes a coral reef. Now, maximum growth does not occur when the reef reaches sea level. Sea level is a limit to coral growth. Maximum growth occurs when it's below sea level. And notice many reefs in the world have a sharp drop-off right here. That's because the coral reef is growing this way. And as the water gets deeper and deeper and deeper, it forms this natural cliff. My first dive ever in open water was in Belize. It was my nicest scuba dive in my life. I've never been able to repeat it. We jumped off the boat. I was a brand new scuba diver. It was 80 feet of water. I thought I was standing on the bottom. And then we swam out over the reef drop-off. And I was in 80 feet of water. The bottom was 300 feet deep. And it looked like I could reach out and touch it. I could see the bottom. Swimming in glass. But of course, I would have died before I even got halfway down. Water's neat stuff. Now, I said that the sea level restricts coral growth. There are places in the world where coral reefs at extreme low tides are exposed. This is in Western Australia. This probably occurs a couple of times a year. Maybe storms help us out. We have high tides and low tides and extreme high tides and low tides depending on the moon cycle. Well, this happens in the middle of the day in the summertime. A lot of corals are going to die. And this happens regularly. And then some more might grow up for a couple of months, and then they might die again. But this is a huge beautiful, luxuriant reef that just happens to be right at sea level. It cannot grow any taller. Well, this topic goes all the way back to Charles Darwin. Did you know that Charles Darwin wrote a book on coral reefs? An entire book on the subject called The Structure and Origin of Coral Reefs. This actually predates the origin of species by 17 years. I love this book. I've read this. It's wonderful. It's this guy walking around all these tropical coral atolls in the Pacific. He has no idea what's going on. And he's coming up with theories and ideas, and what about this, and what about that? And he's exulting in this exploration of the unknown. And he came up with something that's now wrong. This is Darwin's theory of atoll formation. We have, he's basing this on Lyell's geology. And Lyellian geology, no geologist today believes, as far as I'm aware. Lyell had the continents slowly rising and slowly sinking over millions of years to explain all the geology in the world. Well, today, geologists believe in horizontal movements called plate tectonics. This whole vertical sinking of entire continents, I'm not so sure about that. Anyway, Darwin based this idea on that. He has a volcano or mountain sticking up out of the sea, and you can see a fringing reef is starting to develop right here at sea level. Now, if the water surface goes up or the mountain goes down, same result. We have number 2. Here's a new sea level, and notice this reef has developed. There's even little palm trees on the reef. This is now a barrier reef. It went from a fringing reef to a barrier reef with a lagoon. Now, if the water level ever gets this high, suddenly there's no more mountain, and we have an atoll, which is a ring-shaped structure in the ocean with a lagoon in the middle. It is not hard to find examples of this. You can see these all over. Even cute little animations that says that, oh, this process takes 20 million years or 30 million years for this to happen. Well, the problem with this is that Darwin was flat wrong. Now, back in 1887, the Duke of Argyll, he was a political commentator, a very rich man. He was also a scientific commentator. And he wrote an essay called A Great Lesson. And he was talking about a scientific reign of terror at the hands of the evolutionists, waged against everyone who didn't agree with evolution. And in getting at the idea of evolution, he used Darwin's coral reef theory as an example of a bad theory that was ardently defended for decades, but turned out ultimately to be wrong. And he pointed out that the Challenger expedition of the 1870s, the ship went all over the world's oceans, and they drilled all over the place. And they drilled through several coral reefs that were sitting on mud, which completely contradicted Darwin's theory. Well, how come you still see all these representations? Well, I'm not sure, but 120 years later, it looks like modern science is slowly catching up. In 2006, Purdy and Winter performed a study. They compared lagoon depth to rainfall on nearby land. They found a lovely correlation between the amount of rain and the depth of the lagoon. Why? Because rainwater is slightly acidic. It dissolves calcium carbonate. So the more rain you get, the deeper your atoll, the deeper your barrier reef, the deeper your lagoon gets. That's interesting. A year after that, Nakamura and Nakamori published a geochemical model for coral reef formation. And they modeled what would happen in a stable sea level and a changing sea level. And, well, they claim that a reef will naturally develop from a fringing reef to a barrier reef with or without any change in sea level. And that's true because the animals on the outside are getting all the calcium carbonate. They're getting all the food. The animals on the inside aren't getting the calcium carbonate. They're not getting the food. The sunlight is heating up the lagoon to temperatures above where corals can survive. And so we have degradation in here, and we have growth this way out here. Therefore, you naturally would get this formation with or without a change in sea level. Duke of Argyll again. And here we learn the important lesson that an hypothesis may adequately account for actual facts, and yet nevertheless may not be true. It just took science 120 years to catch up. Now, why am I doing this? It's because of this challenge right here in 1 Peter 3:15. It's a commandment, very awkward, very difficult commandment, because we're commanded to do this. It says, "In your hearts honor Christ the Lord as holy, always being prepared to make a defense to anyone who asks you for a reason for the hope that's in you. Yet do it with gentleness and respect." Now, you've heard that several times this week. I use this verse in every single talk that I give. This is my MO for the creation movement. We're commanded to defend our faith. And coral reefs is a big question because it's a big challenge to explain how giant atolls out in the Pacific Ocean have formed in a young Earth scenario. And I'm about to help you out a little bit with this. But in order to get at this, we have to refer to the biblical data. Well, what biblical data can we refer to? Well, the book of Genesis and the timeline that we're given. Now here I've summarized some of the dates in the Old Testament, and I've rounded off all the numbers to make it easy to remember. Well, creation is about 6,000 years ago. It's about 4,000 BC. The flood is 1,600-something years after creation. So I put the flood about 2,400 BC. Abraham is about 2,000 BC. Moses about 1,500 BC. David about 1,000 BC. And the birth, death, and resurrection of Jesus Christ spans the turn of the era. So call it year 0. That's the time frame that we're given. That's just a very tight time frame, isn't it? Well, we've got 1,600, 1,700 years from creation to the flood. We've got the 1-year flood event. We've got a couple hundred years after the flood for the world to settle down, the water to drain off the continents, and then we've got 4,500 years since then, maybe 4,000 years since then. That's what we can do. And I think we can do this, but we have to be careful. Now, I'm going to introduce here Taz Walker. He's a good guy. He's a CMI speaker in Australia. He's a geologist. And he's come up with what some people, this is what I call it Walker's flood model. He has here, this should be blank. He has here a timeline. Now, the flood's only a year and the creation's only a week, but I had to put them wide so that I could put the word in there, okay? But this is relative proportions of the amount of time we have in Earth history. Now, after the creation week, we have 1,600 or 1,700 years of the antediluvian period. We have the 1-year flood event, and then the post-diluvial years, 4,300, 4,400 years, depending on how you count things. So, during creation week, we should have some rocks formed. The Earth is a creation week rock. The whole thing. So is the moon. But in those years, those over a millennium and a half after creation and before the flood, we have the antediluvian period, we should have some formations form. We have rivers draining continents that are dumping dirt out into the ocean, forming laminated structures. We have animals that are calcifying animals, like all sorts of different things, crinoids and things that might be shucking off shells. We have sharks losing their teeth. We have clams, and since death had come into the world already, we have death ensuing. So we should have some rocks that are antediluvian. Now, which ones? I'm not a geologist, remember? I can just talk about this. But Taz has divided up the flood into 2 main stages. The inundatory stage, it's hard to say, the inundatory stage when the waters are coming up, and the recessive stage when the waters are going down. And it breaks up the inundatory into the eruptive, where the water first bursts forth. And then the ascending phase, when the waters are coming up. The zenitic phase, when the waters are up and they haven't yet come down. And he breaks up the recessive stage into the abative stage, when the water is draining off the continents, flowing in sheets and probably carving flat sheet-like erosional patterns on much of the continental surfaces. And then the dispersive phase, when the water gets shallow and channels and carves things like Grand Canyon and places like that. Now, after the flood, we've got a certain residual time. You wouldn't expect the flood just to stop and everything's finished. No, because you've got no plants on the continents. And so any rain is going to wash lots of dirt and mud down. You've got a lot of sediments that aren't solidified yet, and there's water in there. So if you have a cliff, you might expect sapping and a sudden bursting forth as a weak lower layer gives way and all the water comes out. You might have a bunch of erosion and continuing volcanism and things like that. And then you have the modern time with occasional volcanoes, river deltas, lake bottoms, ocean basins, and so you get a continual deposition, but a slow deposition. Now, I tried here to put these in relative proportions of how much a geologic column we might expect. Notice I put more in here than most people do, because for reasons I'm about to explain. I believe that most of the enigmatic coral reef questions that we can address can be explained here in the residual period. Now, I could be wrong. Some of these could be antediluvian. Some of these could be during the flood, but it's only a year long, and we have all the modern stuff. But there are coral reefs up on top of land that we have to explain. And we're going to have to delve into geology. We're going to have to learn the difference between a coral, like this fossil coral. I found this about 10 miles inland of Naples, Florida, on the ground. In fact, they were digging a lake for a subdivision, and they're grinding up the rocks and making driveways and stuff at it. And I knew that that subdivision was sitting on top of an ancient coral reef. So no one was there. I drove my truck in there, so whoop, 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 with all these nice coral colonies, and I drove away. I think I might have done something illegal. I'm not sure, but I don't think so, because they're just grinding them up. Nobody cared. So that is a coral that I collected on land. But then there are coral reefs, like this one. You know, the best way to identify a counterfeit bill is to learn what the real thing looks like, right? So let's look at what a real coral reef looks like. This is an outcrop of the Key Largo limestone. This is in the Windley Key Fossil Reef Preserve on Windley Key in the North Florida Keys in Florida, of course. You're looking at a coral reef, but it's 17 feet above sea level. So obviously, if this is a coral reef, it grew when sea level was higher than it is today. Well, when was that? The rock inside this coral reef is about 30% coral, mainly the Montasteria boulder coral and the Diploria brain coral. Now, in between the corals are sediments, and they fused into stone. And so many things of this, including the species, look just like what we see offshore. These reefs that I've dove on 400 or 500 times. Looks just like what we see offshore. So this is a real, live, honest-to-goodness coral reef that's been marooned above sea level. But one difference between this coral reef and the one offshore is that in between these corals are meant a lot of fine-grained sediments. You don't find a lot of fine-grained sediments offshore. So there's something different about the hydrology and the environment that these corals grew in, but the sea level wasn't just 17 feet. It was probably 30 feet or more higher, because these typical corals grow in about 30 feet of water. They don't grow typically right at the water surface. Now, if you were to look at the geology of South Florida, you're going to see some very interesting things. First of all, Florida is a wide platform of limestone that extends far out into the Gulf of Mexico, and then has sharp edges that drop off very quickly to the deep ocean. Most of that is non-biological. It's chemically deposited limestone. And I'm sorry, but I don't believe geologists understand how limestone is formed. There's not much fossiliferous material there. Now, on the crust, on the top, there are fossils on top. That coral that I showed you earlier came from right about there. The Key Largo limestone is there. I used to live right here in the city of Miami. Now, Miami, the original settlement of Miami, was south of the main downtown district on an old sandbar that had been turned to stone. It was a little bit higher than the swampy areas, and there's less mosquitoes up there. So the original settlements down there were up on the highest land, 2-3 feet higher than everything else, but it was a little bit better than down in the swamp. But you can see, look at this pattern. These are old sandbars that have since been turned to stone. In fact, I went outside in just near my front yard on the way to the grocery store. There's a cliff that's exposed, maybe 10 feet high. And I grabbed a chunk of the rock and I brought it back to my laboratory, and I took this photo of it under a microscope. This is called oolite, or egg rock. Egg rock, obviously, because the little grains look like eggs. This is not sand, like silicon dioxide sand. This is calcium carbonate. And it only forms in very warm water, because calcium carbonate is strange. It has the opposite solubility of everything else. Calcium carbonate is best soluble in cold water and least soluble in hot water. And so in shallow, warm water, a little particle floating through the water will be coated with calcium carbonate, and then another coat, another coat, another coat, and eventually it's too big to float, and it falls out of the water as an a little egg. Well, if we look at the lower Florida Keys, we can see the same shoal pattern, the same sandbar pattern. In fact, you've heard of Key West, right? Most people have heard of Key West, Big Pine Key, all these other keys that are down there. Well, these keys are actually old sandbars that have been turned to stone. And if we look offshore of Florida, I tried to make this, I think this is actually very accurate. The Bahamas are not far away from Florida. In fact, they're just over the horizon from Miami, not too far away. But the Bahama banks are massive shoals, massive sandbars of oolitic sand that has been turned to stone. How did they form? Well, the evolutionist says that they formed slowly over millions of years, and as the weight of sand accumulated, it pushed down the continental crust, or the oceanic crust, so more of it could form. Well, that's interesting, but there sure is an awful lot of it. That's very deep water. There's a lot of calcium carbonate all around the world that was not formed by biological processes, and much of that is up on top of the continental surfaces. Something very strange happened in the recent past in Earth history to form all that calcium carbonate. And recent, I mean, because it hasn't all dissolved away by rainwater and washed back into the ocean. It's not that old. I don't believe it's millions of years old. What could that thing have been? Well, I think that thing should have been Noah's flood. Now, you may have noticed by now that I'm advocating changing sea level. In fact, I'm advocating radical changes in sea level, starting, of course, with Noah's flood, which completely flooded the continents. But after the flood was over, I don't expect sea level is going to reach the modern average for centuries, for several reasons. One, most people know that as water gets colder and colder and colder, it gets more dense. And as it gets just above freezing, it starts getting less dense, and that's why ice floats on water. But what most people don't realize is that water gets less and less and less dense the warmer you get it up. If you took a column of water several miles deep, like an ocean, and perhaps Noah's flood warmed up the oceans, which they should have. Well, if the oceans are 20, 30 degrees Celsius and they cool off to the modern deep ocean average, that's going to drop the water surface by tens of meters just from cooling. Now, if you saw Dr. Silvestri's talk earlier, he was talking about the injection of magma into the crust, lifting the crust up in these large igneous provinces and lifting land above the ocean. And then as that magma cooled, the land went back down to the ocean again. Well, these large igneous provinces all over the world are going to really mess up sea level. So cooling of water, cooling of rocks, sea level changes. But there's more than that. A lot of creationists have talked about the Ice Age. We do believe in the Ice Age. Tomorrow or Thursday when we go on the geology excursion, we're going to look at an Ice Age feature. Well, there's abundant evidence of ice building up on the continent. I have been here, I have been right there, and I grew up right there. There's abundant evidence of an Ice Age. Well, creationists say, how can this be? And they say, the flood would have been the deriving force for the Ice Age. The flood would have produced the heat that caused the evaporation that allowed for all the snow to build up. And when the heat ran out, the snow ran out, the Ice Age would have ended. Now, that's a whole other topic. We have information on our website about that, a couple of books and DVDs as well. But think about this. That much ice would drop the water level in the tropical regions by about 300 feet. 100 meters. Every coral reef in the world today would have been exposed land. Every coral reef in the world today, unless it kept up with sea level increase, according to the geologists, any coral reef on shallow continental margins, which is most of the coral reefs in the world, except all the ones out in the Pacific Ocean, the atolls and things, would have been exposed during the Ice Age. Now, the evolutionists tell us the Ice Age ended about 10,000 years ago. I'm rounding the number off. Well, most creationists would say that the Ice Age ended 4,000 years ago. The difference between 4,000 years ago and 10,000 years ago is not much difference at all if you consider all the unknown factors and all the guesswork and all the assumptions that are going into the production of those numbers. They're essentially the same number. The Great Barrier Reef was dry land just a few thousand years ago. Oh, I remember when I learned that in grad school, I was like, what? There's an evolutionary paper. It's like, yes, that's exactly what I wanted to know. In fact, if we look at the Great Barrier Reef, this is a cross-section of the outer slope on the edge of the reef, not all the inshore stuff, in one particular place. We can see that there's the typical shelf edge about 49 meters down, but then there's a 97-meter terrace and a 116-meter terrace carved by waves, meaning the Great Barrier Reef was way above sea level. But not only that, it means the waves were not strong enough to completely wipe out that hill, and that they weren't there long enough to completely flatten that hill. It must have been quick, or this wouldn't be there. We would have no Great Barrier Reef. It would just be 100 meters deep water with hardly anything on the bottom. Now, I'm wondering if this might be the source of some of the so-called epiric seas that geologists tell us covered much of the continents in years past. Now, I know that Noah's flood would have deposited many marine creatures up on top of the continents. That's standard creationist geology. And that's probably the source of most of the evidence of these so-called epiric seas, but a post-flood high water stand is a possible explanation for some of this data, and I suspect a lot of the regions of the world were flooded for a long time. In fact, it looks like water levels used to be about 80 feet higher. That's what, 20-something meters for you who can't translate. I probably translated wrong, so I can't do it either. But about 80 feet higher than they are today, meaning most of Florida was underwater. Half of Georgia was underwater. A good portion of Texas was underwater. All the low-lying areas underwater. In Georgia. There are three big towns, we call them cities, right in the middle of the state, on the east, the west, and in the middle. And it's called the Fall Line. There's a ring of sand hills that connect these three cities, and it goes on into Alabama, and it goes on into South Carolina. The sand hills are the old shoreline, hundreds of miles from the coast. But then, during the Ice Age, the water level drops. And this is about the time when man is spreading out across the planet, Tower of Babel time. So man now can walk almost through the entire planet. He could get to Ireland if it wasn't covered in ice. He could get to Tasmania in Australia. He could get to the southernmost tip of South America without hardly ever have to crossing any open water at all, no large stretches of open water. And so man would start building cities, as they do, in river mouths and bays and estuaries, and what happens when the Ice Age ends? All the early works of man are now destroyed. Interesting. That's a little bit of a side. Let's get into the coral fossil record, shall we? Most ancient reefs, interestingly enough, are not made up of scleractinian corals. They're made up of things called rudist bivalves, which are little clam things, big clam things sometimes, or sponges, or algae, or the extinct rugose and tabulate corals. Now, the rugosa and the tabulata are not like modern corals. They have a different number of septa, and we assume a different number of tentacles. They have a different growth pattern. Corals actually are bilaterally symmetric, even though they're round polyps. When they settle, there's a main mesenterial filament, and a main portion of skeleton lays down first, and then the other things fill in. So there's a top to a coral, even though it's a circle. These guys weren't like that. Corals, modern corals, they exude a form of calcium carbonate called aragonite. These guys exuded a form of calcium carbonate called calcite. So there are basic biochemical differences, basic biological differences. There are a lot of differences between these guys and the scleractinian corals we have today. And if you look in the fossil record using the evolutionist numbers, the evolutionary fossil record, the rugosa and the tabulata went extinct at the Permian-Triassic boundary, the end Permian extinction event they call this, at the end of the Paleozoic. Then there's a gap of several tens of millions of years, and the scleractinia appear in the middle of the Triassic. Now, interestingly, except for some of the extinct forms, when you find a scleractinian coral from back here, you don't know what species it is, but you know what family it is. Oh, that's of this family, that's of this family. Because the species they kind of ebb and flow over time, but the families are boom, 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 like a whole bunch of sticks in a family tree instead of a nice branching structure. In fact, for a while, some of the coral reef guys, and girls, they were wondering if the scleractinians weren't polyphyletic. In other words, they didn't have different evolutionary ancestors. Maybe each family arose independently from a soft-bodied anemone or soft-bodied ancestor. Well, today with genetics, actually they do form a group because they have commonalities in their genes all together. So it looks like they would now say they're monophyletic. They're one family. So most people are saying they evolved once and then spread out. But it's not borne out by the fossil record. They appear, boom, families, all of a sudden. Now, if we look into geology, we find things like the claim that there's a Cretaceous reef belt around the world, where we have reefs growing in latitudes that they don't grow today on land, or what is currently land. Now, looking at this, it's nearly impossible to tease apart the evolutionary data, the real data from the evolutionary interpretation. Now, some of that, though, might be due to the growth of coral reefs on what's now land after the flood. I had a roommate when I was in grad school. He was German, and he's a geologist, and he went on a field trip to a mangrove island off the coast of Key Largo. And he came back and he was all excited about what he found. And I was like, what, you found sandflies? Oh, no, I'm so happy. Well, you're happy to be bit by mosquitoes? I mean, why would you go to this mangrove island and be happy? Well, because the mangrove island was connected to the mainland, it's only a few hundred yards, by a mud bar. But the mud bar was covered in corals. Corals related to Porites porites. The corals probably Porites divaricata. It's almost the same thing, but a little skinnier. It looks like that. Covered in it. He said, I finally have a way to explain the coral reefs from home. I said, you're from Germany, man. What do you mean coral reefs? No, it turns out there are many coral reefs in Germany And farmers still today, when they're plowing, they kick up pieces of coral from the ground. Well, when did they grow there? Perhaps after the flood, when water was high stand. And what he was so excited about, his explanation was, this particular species of corals grows in muddy, backwater, still hot environment. And he says that must have been the environment in Germany. I don't have a problem thinking that there was a backwater on the continent for several decades or several centuries after the flood. Coral reef grew there, not a big fat one, just a crust of coral. I don't know how thick it is, but I don't imagine it's hundreds of meters thick. And then the water either evaporated or drained away, leaving a dead coral reef. Now, several million years before this, in the evolutionary model, that we have what are called Triassic reefs. Now, these look very much like reefs. The top one is in Austria. The lower one is in North Africa, on land. Well, maybe these are real reefs, but if so, they're post-flood. Or late flood, post-flood. Now, after the flood, I think we probably have several centuries to work with before the end stages of the flood stuff is finally finished. And I want someone to go examine these. We need people on the ground to go check these on a case-by-case basis and say, wait a second, this is what the evolutionists said, here's what it looks like, but wait a second, how do you possibly explain that? And this happened actually a lot in creationist geology. So what I'm going to do now, I'm going to bring up 3 case studies. These are tricky puzzles. These evolutionary arguments for these seem very strong. And as I go through these, we're going to have to put on our thinking caps. So 3 case studies. And, I'm indebted to 2 people. One, Ariel Roth. He's a young earth creationist. He wrote a lot in the 70s, a little bit in the 80s, not so much in the 90s. I don't know the man, but I am indebted to him. He did a lot of coral studies. In fact, I've downloaded a lot of his papers that he wrote in the secular literature because he was doing stuff that I used to do, and that's very fascinating. But I'm also indebted to a man named Dan Wonderly. He is a Christian, but he's an old earth Christian. And he wrote this book called God's Time Records and Ancient Sediments, Evidences of Long Time Spans in Earth History. So I am indebted to these 2 men because I chose 3 examples of things I want to talk about, and both of these guys wrote about all 3 of them. So I get to read their contrasting views. Well, this is a map. Actually, when I was in grad school, I went up to a world-famous coral reef geologist, and I said, Dr. Blank, I said, I've got all these examples of coral reefs all over the world, and all these examples in geology, but all the ones that I know are close to the surface. Do we have any coral reefs that are buried way deep underground, like a mile underground or something like that? And he looked at me funny, like, why would I ask such a silly question? And he goes, oh, yes. In Canada, there are coral reefs that they use for oil prospecting. And they're deep underground. I said, ooh, okay. Well, Dan Wonderly happened to write about it. They're here, Alberta, British Columbia area. He gave me a lovely cross-section. He said these are reefs deep underground. But I started thinking about this and said, I'm not so certain. You see these red arrows here? Those are the reefs rising straight up out of the ground. And I started asking questions. I put on my thinking cap. First of all, reefs don't grow vertically. Reefs grow in the direction of the tide, the current, the wind, the waves, the food, the sun. They don't grow straight up. Second of all, if they're growing up, they're probably going to flatten out and spread out. Third of all, how come no new reefs started popping up in this area if they could grow there? Fourth, there's no framework builders. To have a modern reef, you need corals there to hold the stuff together so that dirt can accumulate and weld into an old structure. There's a few scattered fossils in there, but it's mainly just mud. And even more important, this basin is filled with what are called evaporites. If you take seawater and evaporate it, the first thing that forms on the bottom is crystals of salt. They call that halite, salt rock. Then next you'll have a band of anhydrite, or calcium carbonate. And next you'll have a band of dolomite, or magnesium calcium carbonate. And this basin is filled with alternating layers of these 3 things for hundreds, if not thousands of feet. Now, wait a second. Animals cannot live in seawater that's evaporating down to nothing. How do you get a reef growing in this area? And how does a reef grow at the same time as thousands upon thousands of seawater intrusions are occurring and then evaporating? You would not get a reef. As a biologist, this makes me very, very uncomfortable. And Taz Walker had a very interesting article in Journal of Creation 11 years ago. He talked about fluidization pipes. Now, this structure here is stuff that was oozed up from a lower layer. This layer of rock was laid down on top of a lower layer of rock before the lower layer of rock turned to stone. And the overburdened pressure squeezing down the stuff underneath, which was still soft, found a weak spot and squeezed up like a tube of toothpaste. This is the same thing that happens during thunderstorms. The cold air pressing down, the warm air rising up, there's instability, and all of a sudden the warm air finds a hole to poke through, and it pops up and makes a thunderhead. Well, I'm wondering if these things aren't giant fluidization pipes. Either way, they're not reefs to a biologist. Okay, number 2, the Capitan Reef of Texas and New Mexico. You might have heard of Carlsbad Caverns. Carlsbad Caverns are dissolved into that limestone. And look at this. We have what looks like a reef. We have significant relief. We have a hill. It's made by sponges and other things. Wonderly again. If you look at it, looks like there's an embayment. Should have a lagoon. There are cavities with sponges in it, and the sponges are growing down, and since then they've been filled up, and et cetera, et cetera, et cetera. The evolutionists are saying, this is a reef, this is a reef, this is a reef. What do we do with this? Well, we put on our thinking cap and we start asking questions. First, just like the previous example, so as a cutaway view, this basin is filled with evaporites, as you can see in these drill cores. Living animals can't survive in evaporative basins. And not only that, but as this basin is filling in with these evaporites, wouldn't that change the hydrology? Wouldn't it, and all of a sudden the ground is coming up and you need the water to wash in again and again and again, but the ground is getting higher. Wouldn't it change something? And where's all the volcanic material, the volcanoes that are going to go off during this millions of years process? And where are the animals that came in here and died? And where are the land sediments from the land that was washing down into this, which had to have happened? It's not there. Well, how do we get evaporites? I think that evaporites, now I don't know, it's a theory of mine, that these so-called evaporites are actually deposited by hot geothermal fluids that come out of the ground and lose their calcium carbonate and salts. And we get rapid layers forming quickly, because I cannot explain that even in an old Earth context. It doesn't make any sense to me. Ariel Roth. One of the main problems with the traditional reef interpretation of the Capitan Reef complex is a lack of reef frame builders. The massive reef core consists mainly of fine calcium carbonate mud. The robust, wave-resistant reef frame builders of our present reef are missing. Another example of no framework builders. Okay, number 3, probably the most challenging, and then we talk atoll. It's part of the Marshall Island chain in the South Pacific. You might be familiar with it if you know anything about the theater of operations in World War II. And even after the war, and Eniwetok was made famous by the U.S. military, who decided to try to blow it up multiple times with atomic weapons. But before they did that, it was made even more famous because they sent a drill team out there to core it. And they drilled 2 cores all the way down through 1,400 meters of reef material before they hit hard rock. This atoll is sitting on top of a 2-mile-high volcanic mountain. And above the mountain is more than 4,000 feet, 1,400 meters of carbonate rocks. Those rocks are claimed to represent over 40 million years of slow subsidence. In Darwinian fashion, the mountain is slowly subsiding, the reef is slowly growing, and it can keep up just fine. Wow, that's a challenge. Cross-section of the reef. Now, these actually are stylistic. That's not really where they drilled the cores, but based on the coring data and based on a lot of echo reflection of seismic data, it looks like this, and that looks very much like reefy sort of stuff. How do we get that? Well, maybe it is a coral reef that grew extremely quickly. I mean, we don't know how fast corals grew 4,000 years ago, right? Well, actually, I don't like that argument. That makes me really uncomfortable. I mean, yes, some corals grow fast, but most don't. Yes, conditions were different in the past, but not that much, especially out in the middle of the Pacific Ocean. But notice what's going to happen here. As a prevailing current hits the side of this underwater mountain, it's going to deflect upwards. In fact, some studies have shown that sand grains on the side of many seamounts actually migrate upwards. So all of a sudden, the growth of the coral reef might not be dependent upon the growth rate of the coral, but the rate at which the sediment, the small coral fragments and the algal fragments, get piled up on top of this reef structure. And so all of a sudden, oh, okay, well, maybe it can keep up in a young Earth framework. Still a lot of growth, though. But notice also the atoll is sitting on top of a volcano. If there's any latent heat in this volcano, it's going to cause convective cycling of seawater through the reef structure. The reef structure is very permeable. Those drill cores that they drilled, the tides go up and down in the water in the hole. which means it's connected to the ocean. And maybe that volcano is releasing calcium-rich water, also percolate through the thing. Now, I don't know which of those is true. Of all the scenarios, I like number 2 the best. I like the idea of seawater flowing and piling up material on top of the seamount. I would really like to see that modeled. I don't have the technical expertise to do that, but that's my hypothesis right now, that we can explain rapid growth of coral reefs just using physical means like that. Now, the last subject I want to cover is the recent degradation of coral reefs worldwide. The professors that tutored me in coral reef ecology, they told me stories that were unbelievable about corals here and how big they were and how they looked and amazing stuff. Well, in my few years in grad school, I was able to tell similar stories to the new graduate students that were coming in when I was leaving. Because after those 6 years or 7 years in Florida, I watched a lot of things die. And I can say, man, you should have seen that reef. You should have seen that coral. You should have seen that spot right there. It was amazing. Now it's all dead. Well, why is this? Well, part of this is because corals thrived in the post-flood world. The conditions right after the flood obviously were rich for coral growth, or they wouldn't be there. Second of all, conditions have changed. The flood was 4,500 years ago. The biggest perturbation of the environment in Earth's history was 4,000 years ago. Things have changed since then. But see, the coral reef is a complex microenvironment. And the complexity of that environment allowed it to persist even after the conditions that allowed it to grow in the first place changed. And so it held on and held on and held on. But now, after all these years, it's starting to give up. And the combination of modern environmental stress and anthropogenic, that means man-made, anthropogenic stresses are pushing a lot of reefs over the edge, especially in Florida and other marginal reef areas. Look at what Genesis 3 says. It says, God talking to Adam after Adam rebelled against God. God said, "Cursed is the ground for your sake, and toil you shall eat of it all the days of your life." But it's not just the dirt that's cursed. Oh no, Paul explains that very clearly in Romans 8. He says, "For we know that the whole creation groans and labors with birth pangs together until now." That's the entire universe, suffering and groaning under this weight of sin. We should therefore expect decline over time. Combine that with the after effects of Noah's flood, we should doubly expect decline over time. But at the same time, us humans were put here on this earth as stewards. How do we reconcile the decline with our stewardship? By soberly assessing the data and making an informed decision about what we're looking at. Now, after I've done that, I don't believe we can save coral reefs. Not in the long term. Everything is doomed. But then again, I don't advocate wholesale pollution of the oceans either. I like to eat fish and I like to get water to drink and stuff like that. But it doesn't surprise me that a complex system like that with a rich and luxuriant history would slowly degrade. Genesis 1:28. This is where we get the creation, some of the creation mandates. God said to them, "Be fruitful, multiply, fill the earth, and subdue it, and have dominion over the fish of the sea, the birds of the heavens, and over every living thing that moves on the earth." Humans were put on this earth to be stewards of God's creation. Now, this is not an environmental wacko thing. That's the Bible. How we answer that, though, there's a diversity of opinion. It's not easy. But you see, our only hope is for Christ to return. Look at Revelation 21. It says, "God will wipe away every tear from their eyes. There should be no more death, nor sorrow, nor crying. There should be no more pain, for the former things have passed away." What are the former things? It's all that stuff that happened in Genesis. It's going to be erased and redone and remade, and we'll have a brand new place to live, and I can't wait. We can't put our hope in the environment. That's a fool's hope. We can't put our hope in science or technology. We certainly can't put our hope in man. Our only hope is in Christ. So to summarize, scleractinian corals are geologically recent. Most reefs in the rock record have no modern comparison. So it's hard to make a comparison between then and, evolution, new things have evolved, and things like that. Okay, fine, but I can't compare modern coral reefs to what are called reefs in the fossil record, especially when you consider that there aren't any giant colonies of corals in the fossil record. Most reefs are small, and the big ones mainly made of mud with no structural framework. Many reefs in the record, therefore, are falsely labeled. We don't need to call for super fast coral growth. I think we should be calling for normal mechanisms based on what we know about the biology of the animals today, allowing a little bit of gray for maybe they were a little more robust in the past, but not that they grew 100 times faster than they do today. And I believe we should appeal to physical mechanisms, and I believe that we can appeal to physical mechanisms to explain this giant enigma called coral reefs. So in the future, here's what we need. We need boots on the ground. We need people going out there to all these places in the world and analyzing it and reporting it and reinterpreting things from a young Earth standpoint. We need Ph.D. and master's level graduate students. Fine, great. We also need regular old people to help because there aren't enough of us. We have to also develop a young Earth creation model for coral reefs. This is just an intro. I kind of made that up. There's a lot more stuff that I didn't address. There's a whole lot of more questions I didn't even get to. But this is going to necessitate an improvement of the creationist models of sea level change, ice age, plate tectonics, the residual flood effects, seawater chemistry, atmospheric chemistry. Coral reefs are a complex subject. They bridge the divide between geology, chemistry, physics, and biology. Wow. But they sure are fun. Now, if you saw in Creation Magazine a couple of editions ago, I had an interview in there, and there was a sidebar of some of my explanation of coral reefs. Well, that was an hour-long thing to explain my 2 paragraphs. So if you want to go and find something maybe to back up what I just said, there's not much to turn to right now. I suspect that after I gave this talk, the CMI is going to have me writing articles now on this subject. Okay, I'll do it. But if you want to get something that was actually in print right now, Geology by Design by my good friend. He lives in Atlanta with me, Carl Frody. And Geology by Design, not only does it talk about the inundatory stage and recessive stage and rocks and fossilization and all sorts of things like that, but he does have a little bit of information here on corals. In fact, pictures of coral reefs and things like that. So it's about the only thing on our things that we have that can help you out. Okay, let's pray. Jesus, thank you so much for your word and for the world and for science. And thank you, Lord, for these really cool things called coral reefs. And even if we don't have a clue of how they work or how you built them, Father, please help us understand them. And Lord, please help us to be wise in approaching the world, to be diligent in sharing our faith with other people, and to be bold enough to be insulted for your name. Amen. Excuse me. Okay. 10 minutes. Questions and answers. Any topic you like. Of course, this is going to be hot on your mind, but I'll take any question that you like. That's a cool picture. I like that. Okay, first. Yes? How long did the Ice Age last, and how long did the Ice Age last is a question of models and mathematics and assumptions based on seawater temperature and things like that. Nobody knows for certain, but the creationist work that has been done has suggested that the ice built up to a maximum several centuries after the flood and lasted for several centuries. The Tower of Babel event is 5 generations after the flood, so it's approximately the right time frame for ice. In fact, if we look at the world today, Europe was one of the last places settled. Because when the Europeans got to Europe, it was covered in ice. And as the ice retreated, then Europeans moved in. So it seems to be a very similar time frame, but I can't put a number on it. In fact, I don't like it when evolutionists try to put numbers on it. Therefore, I don't want, as a creationist, to put a number on it because there's too much that we don't know. Good question. So, yes? How did the coral survive the flood? Good question, thank you, because I meant to put that in there and I forgot. Okay. How did coral survive the flood? Great. Perhaps out in the middle of the Pacific Ocean, corals were just out there. They went underwater a little deeper, the water came up a little bit, and yet they survived that way. There are corals right now that can survive on rafting, like they might attach to a coconut or a log that's floating. As babies, they might grow there. They're water creatures also, so they're in the water already. You know, the flood was designed to kill off all the air-breathing animals and people, not the stuff in the water. I actually wonder, when God created everything, he had to create everything to look old. When he created Adam and Eve, he didn't create Adam to look like a zygote or a newborn baby, right? He looked like a man grown up, probably even with a beard already. He created trees grown up with leaves on them. Now, did they have tree rings inside them? Don't know. Would that have been deceptive of God to put tree rings inside a tree that had no age? Likewise, coral reefs. When God created the coral, did he just create a flat rock and coat it with a coral with a whole bunch of mouths? Or did he create a rock with three-dimensional topography for fish to live in, an entire functional ecology called a coral reef? Well, would that have been deceptive of God to create a boulder that has no history, that looks like it was formed by a coral? So how did they survive the flood? Backwater areas, deep in the water, away from continents, and possibly some rafting, possibly some little planular larvae swimming around, though most of them would have died. Various means, various ways. Most things did not. Many, 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 many species did not survive Noah's flood. Period. Especially marine invertebrates. And corals have no backbones. They're marine invertebrates like snails. They're invertebrates. I don't necessarily know. That is a great question, though. And I do want to explore it further, and I hope someone else actually might help me out a little bit, because I want to know the ancestral source of the coral population that populated the world after the flood. I don't know where they came from. Okay. So, Mr. Evolutionary Geologist who's watching on the internet, yeah, you just saw me get stumped, and it's okay, I don't mind. Okay. Sir? Is that a leading question? The question is it impossible to have an ice age with slow, gradual changes? If I look at the mechanisms right now to explain the ice age, the most common theory is called the Milankovitch cycle, that the Earth has a wobble and has a precessional change, and over tens of thousands, hundreds of thousands of years, depending on which part of the change of the Earth's orbit we're talking about, it'll change the amount of sunlight reaching the Earth, and therefore it'll either drive an ice age or remove the ice age. But we're only talking about a 1 to 2% change in the amount of sunlight based on all these ephemeral things. That's not a lot. In fact, the sun varies by more than that over the short term. Now, interestingly, so I don't know. I haven't seen a climate model that I trust modeling ice ages. In fact, in climate models, at least 5 years ago, they still hadn't added clouds because it was too complicated, because it's very difficult to model the world. Okay. Interestingly, you've heard of global warming, right? Why are people afraid of global warming? Why is it a fear? Well, it's because they believe that small changes in the amount of sunlight striking the Earth can cause an ice age. Therefore, small changes in carbon dioxide level in the Earth's atmosphere can cause enough temperature change to induce rapid climate change. I don't have that fear. Yes, maybe carbon dioxide is warming up the air a little bit, but the Earth is a buffered system. God intentionally built it. He said, seed time and harvest, summer and winter shall not cease right after the flood, right? He's promised us that the Earth is not going to burn up. Now, it doesn't mean it's always going to be comfortable, but I'm not really worried about climate change. Sorry, I'm getting off the topic. Again, I didn't answer it very well. I'm not happy with the models. How's that? And I think Noah's flood is a much better explanation because it gives us a source of heat to cause evaporation. How did grass and other plants survive under the water? That's actually very interesting. Actually, Charles Darwin figured that out for us. Inadvertently, Charles Darwin, who had never actually did a controlled experiment of his life, he did a lot of experiments, sort of. And one time, he took seeds and he submerged them in salt water for over a year. And then he took them out and he planted them and they sprouted and grew. Wow, Mr. Darwin, thank you very much. Plus, after the flood, we expect massive amounts of vegetation floating on the Earth's surface. A lot of seeds in there. I mean, if you went outside here and you covered up a piece of grass and killed all the grass, and you put a dome over that, the next year seeds are going to sprout. If you pull them up, the next year seeds are going to sprout. You pull them up, the next year seeds are going to sprout. The seed bank in the soil is decades long. So seeds can last a long time before they sprout. But many things did go extinct. Now, interestingly, there's no grass in the fossil record. The evolutionists believe that grasses didn't evolve until way after the dinosaurs went extinct, maybe 30 million years ago or so. So where are all the grass? And the grasses almost cover the Earth today. They're found everywhere. None in the fossil record until they realize they're in dinosaur poop. In fact, they found every single family of grasses in dinosaur dung that's now been fossilized. So even though grasses are never buried with the dinosaurs, we know grasses live with dinosaurs, And so they had to redraw all their dioramas that only have tree ferns and mud. Now they have to cover the ground with grass. So, long story. How was someone over here? Yes?
I was hoping that you could comment on the August moon and the population of the coral reef.
Can I comment on the August moon and...
The sturgeon moon and how the coral reef repopulates on that.
You're talking about coral reproduction? Oh, interestingly, part of my job every summer was to go down to the Florida Keys and spend 2 weeks night diving. So many of my scuba dives were at night. That's a lot of fun. At night in shallow water, as long as it's calm, it's okay. But if it's not calm, then you bam into the coral. Oh, man, bam, oh. You're not supposed to do that. You get in trouble if you break the coral. So we try not to hit anything. When you hear pang, you're like, oh, someone hit the coral. Anyway, so corals are very interesting. And they have lots of different ways of reproduction. Some of the biggest corals spend the least amount of time caring for their young. Some of the smallest corals spend the most amount of time. They actually have internal fertilization and the release of fully formed planae larvae, which will swim around and land sometimes right next to the parent. But some of the big corals, they're broadcast spawners. Each one of the little polyp mouths will release a ball. It looks like a little pink piece of styrofoam, and it floats up. And inside that ball, there are, somewhere around 100 eggs and millions of sperm. And when they float to the surface, they break open. It actually makes a slick on the surface of the ocean. But all different colonies, all different species, sometimes at the same time. And so the eggs and the sperm, they have recognition factors. Like, oh, that's the wrong one, that's the wrong one. Ha, boom, and they can fertilize that guy. But they, depending on the species, the Acropora elkhorn coral, they tend to spawn a couple of days after the full moon closest to the warmest water period. So it's usually in August, but if the full moon is not in the middle of August, they might spawn a little bit at the end of July and a little bit at the beginning of September. Or actually, beginning of August, beginning of September. But the star corals, the big mountain boulder corals, they tend to spawn a few days after that. And they really do the same thing. They release all these egg bundles into the water, and I have raised multiple baby corals. I never had one live. They're so small that any little critter on the bottom of the tank just squishes them or eats them. I've had them grow to, about as big as a fingernail and then die. And I was like, oh, man. As far as the broadcast spawners, the planulating corals that only release the fully formed planae larvae, those are a piece of cake. I grew them all the time, like the ones I had to scrape off my fish tank. Is that what you're asking about? Okay. Okay, yes? I mentioned that by the end of my Ph.D., I could cite examples of coral reefs that had gone. Am I suggesting there are less and less coral reefs? Yes. Coral reefs across the world have gone through a tremendous decay over the last several decades and centuries. Part of that is man's problem, part of that is not. And it's hard to tell the difference between the two. There's some places that are still pretty healthy, though. Okay, one more. One more question. Anyone over here? Be quiet over here. Anyone over here? Yes, lady, waving your hands. Oh, if corals are animals, does it hurt when you break pieces off of them? No. They don't have a brain to interpret pain. They do have nerves. In fact, they have a very simple nerve net that connects one end of the coral to the other. In fact, one end of the colony. You hit something over here, and you can watch a whole bunch of polyps in a whole area contract because they're connected with this nerve net. They have neurotransmitters, but they have the ability to detect damage, but not to say, ouch. So my primary research tool underwater was a hammer and chisel. They tell the tourists, don't touch the coral, you'll kill it. And I'm not like, pink, 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 pink. But I had to have a permit for all that, and the permitting process was difficult. And so it wasn't like I was just going out there destroying everything, and I had to classify everything, keep it safe. And so no, they don't feel pain. Okay, thank you very much. I'll be back here at 9:45. But in the meantime, good man Gary Bates is going to come up here and entertain you about 20 minutes from now. Wire cutters and going break and taking some super glue and gluing it to a plastic screw and then putting it in a plastic holder in my fish tank. I grew hundreds of these this way. It's really neat. They're very modular animals. In fact, I grew all of these animals in my lab. Probably a dozen different species. In fact, I grew those sea urchins in my lab. And yes, those spines are pointy, and when they hit your hand, they break off and they leave a black scar in there for days, weeks, sometimes months. And then the next day, you put your hand in the tank, and it happens again, and so that's the life of the marine biologist, I guess. Now, when most people think of coral, they usually don't think of the animal. This is Montastria favulata, the great star coral that forms many reefs in the Caribbean. Now, when they think coral, they usually think of the skeleton. This is a skeleton. We took a hole saw, went up to a coral colony, and drilled a hole in it, and then put it into a piece of PVC and put some clay around it, and it grew up out of the PVC and made this lovely thing. And then a disease came through my tanks and killed this colony. I was very sad because it was 5 or 6 years old by the time it died. I mean, from the original colony. But if you take this and you zoom up on that skeleton, you can see some beautiful architectural details. And sometimes coral colonies or coral species are kind of hard to tell apart, especially if they're in the same family. And so people have taken to measuring these microscopic little details, the width of this and the length of that. In fact, my first paper I ever wrote was dealing with this very thing. I microscopically examined 3 different coral species with my partner, and we concluded some various conclusions about these 3 species. It took a lot of work and a lot of measuring. But they're amazing stuff. Now, one more interesting fact about the tropical scleractinian corals. Now, I just said tropical scleractinian corals. Did you understand what I just said? Can you believe that I just said that word and you understood it? Because 5 minutes ago, you just said what? Okay, scleractinian means hard. The hard corals, the calcium-producing corals. Well, they're actually algae farmers. These little buggers are photosynthetic. In fact, it wasn't until the middle 1800s where people said, oh, those aren't plants, those are animals. Oh, okay, so now corals are animals, and they are animals. But inside them, they have thousands upon. You think rock. I think animal. Like a lot of people collect shells, but very few people consider the animal that used to live in that shell, the beautiful snail. So let's figure out what a coral is. Well, first of all, a coral is an animal. But it's not just any animal. It's a simple animal with 3 layers of tissue and some characteristic stinging cells. Well, that puts it in phylum Cnidaria, along with the jellyfish and the Portuguese man-of-war and hydroids and all sorts of things like that have stinging cells. But it's not just any cnidarian. Corals belong to a group of animals called anthozoans, or flower animals. Now, the anthozoans are broken down into 2 main groups. We call them the hexacorals and the octocorals, because their tentacles come in sets of 6 or sets of 8. The hexacorals, most of them have a skeleton. Most of the octocorals do not. So here we go. If we want to talk about coral reefs, we're going to have to focus on a subdivision of the hexacorals called order Scleractinia. How you doing with these big Latin words so far? Scleractinia means hard anemone. And this order can be broken down to several main families that can be distinguished by shape or color or habitat or behavior. Corals are animals, by the way. They have behaviors, even if they can't move. And some of these animals are stunning in their beauty. A lot of what you see in this photo are scleractinian corals, or recently deceased scleractinian corals. They've got a rich diversity of shape, color, texture. It's amazing animals. They have a lot of things in common, especially at the most fundamental level, because corals follow a basic design that's based on the presence of a polyp. Some corals, like this one right here, are solitary. It's just a single polyp. But if you take that polyp and you split it in half, you can reveal the basic biology of these animals that do amazing things. You can see a ring of tentacles and a central mouth and a simple stomach, a 2-way stomach, so anything that doesn't get digested comes back out the mouth again. Now, if that looks like an upside-down jellyfish to you, it should, because jellyfish and corals have the same basic anatomy. They're both based on the polyp structure. But this particular polyp, being a coral, being a scleractinian coral, is sitting on top of a piece of limestone. It made this rock. In the process of growing, it extrudes calcium carbonate from its lower tissue layer, and as it grows upwards, it secretes calcium carbonate underneath it, so the animal is actually growing an exoskeleton. We have an endoskeleton. Corals have an exoskeleton. But if you look carefully, you can see these two things of tissue to the side, and these are going to connect to the next polyp in the series. Well, that raises some interesting questions. See? That raises some interesting questions of what actually a coral colony is. Well, we're stuck with this polyp-based form. Therefore, corals are limited in how large they can grow. This is an example of a large mushroom coral, maybe 6 inches, 20 centimeters wide. That's about as big as they can get, a little bigger sometimes. But you'll notice already that his mouth is being distended because he's trying to adapt to this huge thing with all these tentacles that are passing food into the mouth. So corals, because they're in the polyp structure, they can't get much bigger than that if they keep that form. And so, in order to get larger, very often this one animal will divide itself up into a multi-mouthed sheet of tissue. Now, the animal's only a few millimeters thick, but it can cover a large surface area. I have seen single coral colonies larger than this stage, several meters in height, that made a whole patch reef all to themselves, and it was just one giant colony with thousands upon thousands of mouths, but one animal. So really interesting. They're not like normal animals. Normal, whatever that means. Now, corals come in many shapes and sizes. This beautiful specimen is my absolute favorite. This is Dendrogyra cylindrus. They have their tentacles out in the daytime, and they wave in the wind. It's absolutely amazing animals. And you can notice that this animal has sent up these stubby branches to increase its surface area, so it can capture more food, capture more light. Here's another branching coral. This is Porites porites. I grew this one in my lab by taking a pair of thousands, and you can see this brown. Can you see the polyp here? This is a baby that I collected in the wild, and I settled, and I took this under a microscope, and all these little dots in there are called zooxanthellae. They're algae that live inside the coral. Under a special microscope, I took this photograph. This guy here is only about 1 millimeter or 2 tall. This is tiny. This is actually from a colony of Porites asteroides with little teeny polyps. And you can see this reddish glow in here. That's from the chlorophyll that's in all the zooxanthellae that live in the coral. The zooxanthellae take sunlight, and they convert it into sugars. Carbon dioxide, sugar. The coral says, yum, yum, thank you for the sugar. The algae says, yum, yum, thank you, or thank you very much for a place to live. Now, there's some debate about whether the zooxanthellae infect the coral, if the coral has a zooxanthellae in prison. But no, this is a symbiosis, a beautiful relationship that allows these animals to live in what is otherwise a desert. Because there's no food in the open ocean. There's hardly any nutrients in the open ocean. It's the world's giantest desert. And yet, if you go into the open ocean, you can find a patch of ground that's close to the surface, and it was probably, at least in the past, would be covered with scleractinian corals. You know, the more I learn about these animals, the more I want to shout with the psalmist. For you, O Lord, have made me glad by your work. At the works of your hands I sing for joy. Beautiful. Now, we know what a coral is, right? Not just a rock, it's an animal. Let's talk about what a coral reef is. But first, let's define what a reef is. See, the question of what is a reef depends upon whom you ask. To a biologist like myself, a reef is a community of organisms. I'm more concerned with functional ecology. So a 2,000-year-old coral reef has about the same functional ecology as a 100-year-old lava flow that has corals that have encrusted, and sponges and algae and fish have recruited to it. It looks about the same. You can't tell from the surface necessarily which one is older. But to a geologist, they will give you a very different answer. Geologists are concerned with structure, shape, form. So to a geologist, a reef is something in the rock record, usually made of limestone, that appears to have been made by living corals or clams or algae or sponges, that has some thickness to it.
Well, we've had Dr. Rob Carter speak once before, so I'm not going to go through his bio. But we're in for a treat tonight. If you've caught his first session, it was fantastic. He's going to give this talk, and then we're going to have Gary Bates come in and give you an alien intrusion experience. And then Dr. Rob Carter is going to come back again this evening for that night owl session, that special talk that isn't in your schedule. So 9:45, you're going to want to come back from that because he's got some mind-blowing stuff he's going to share. So why don't you guys give it up for Dr. Rob Carter.
Well, as you all now know, my name is Robert Carter. You're about to hear a story that has taken me more than 20 years to put together. This goes back to my, with my first 200-gallon saltwater aquarium. Then to my over 500, I lost count at 500, but over 500 scuba dives in Florida and Belize and the Bahamas. And eventually to my Ph.D. in coral reef ecology. Now, this has not been an easy process, however, for I've had to unthink much of what I previously learned. Much of what I learned contradicts the history given to us in the Bible, especially the creation account. You know, the book of Genesis tells us in beautiful narrative how God created the entire universe in 6 days about 6,000 years ago. During that 6-day work week, God first created light, and then time and space. Then he separated the oceans from the skies. Then he filled the land with plants. Then he created the heavens with the sun, moon, and stars. On the 5th day, he filled the seas and the skies that he created 3 days earlier. Likewise, on the 6th day, he filled the earth with animals, and then his ultimate creation, man. But we're going to focus on day 5 of creation week. Genesis chapter 1, verses 20 through 23 says this. And God said, let the water swarm with swarms of living creatures. So God created the great sea creatures and every living creature that moves with which the waters swarm according to their kinds. And God saw that it was good. And God blessed them, saying, be fruitful and multiply and fill the waters in the seas. And there was evening and there was morning, the 5th day. Okay, so we're going to talk now about some of the creatures that God created on this day. We're going to talk about one specific group of critters, but most people don't know what I mean when I say the word coral.